Welcome to the hands-on workshop, Performance Optimization for Intel Xeon Phi Processors. This is episode 1. My name is Andrei Vladimirov, and I'm the head of high-performance computing research at Colfax International. This workshop comprises two parts. In part 1, I will talk about the organization of Intel Xeon Phi processors and what it means to the programmer. In part 2, I will run several hands-on demonstrations on performance optimization for this platform. Because this workshop is not long enough to discuss all of the details, in the last episode, episode 10, I will give you pointers on where to learn more. Now we are beginning episode 1, Intel architecture. Intel makes a variety of processors, and you have probably worked with an Intel Core processor or an Intel Atom or a Pentium in a desktop or in a mobile computer. If you've worked in a data center or in a cluster, you probably were using Intel Xeon processors. These are enterprise-class Intel CPUs. Together, all of these processors form the multi-core architecture because they feature multiple execution cores in each chip. And this architecture is general purpose. This means that you can use this architecture for computational applications, and you can also use it for running applications such as web servers or data management or running consumer applications. In addition to the multi-core architecture, Intel recently introduced the Many Integrated Core or MIC architecture. This architecture is specialized for computing. Representing this architecture are Intel Xeon Phi processors and coprocessors. The first generation of Intel Xeon Phi was introduced in 2012, and you may have heard of it by its code name Knights Corner or KNC. It was available as a coprocessor, so it was a PCI Express add-in card, and you had to have a system with a host CPU, usually a Xeon, to run one or several of these coprocessors. In 2016, Intel introduced the second generation of Xeon Phi, and you may have heard of it in the media by the code name Knights Landing or KNL. It was introduced as a bootable CPU, meaning that it does all the things that a normal CPU does. It boots the operating system, it controls the main memory, storage, and networking. And at the same time, this is a specialized architecture for computational applications. Even though the MIC architecture is specialized, it doesn't mean that you have to run specialized hardware, specialized software on it. Indeed, the idea behind the MIC architecture is that you have a single code base, and if this code is developed with modern code practices, then it will run effectively on general purpose Xeon processors, or for that matter, Core or Pentium processors, and at the same time, after recompilation, this code will run effectively on the MIC architecture. The reason to use an Intel Xeon Phi processor is its performance. Inside of every chip, depending on the model, you will find between 64 and 72 cores with 4-way hyperthreading, and these are Intel cores with vector instruction support inside of them. They are clocked between 1.3 and 1.5 gigahertz. Just from these numbers, you can understand that this is a specialized architecture. First of all, this is a high number of cores, so you should expect high performance. At the same time, this is a low clock frequency, so you can expect high power efficiency. And indeed, the thermal design power of most models of Xeon Phi processors is between 215 and 250 watts. The theoretical peak performance of a single chip is over 3 teraflops per second in double precision and over 6 teraflops per second in single precision. This is for the fuse multiply add operation, FMA. This operation is relevant, for example, to the high-performance LINPACK benchmark. These processors have access to two types of memory. First, the regular memory that lives on board, based on the DDR4 technology, and you can call it on-platform memory. This memory can deliver over 90 gigabytes per second of streaming bandwidth. The second kind of memory is high bandwidth memory. It is fused directly on the chip, so you can call it on-package memory. And because it is based on a novel MCDRAM technology, it can deliver bandwidth in excess of 400 gigabytes per second. Like many Intel processors, second generation Xeon Phi is binary compatible with its predecessors, particularly with Xeon. It means that you can take an application that is compiled for a Xeon, and even if it uses vector instructions, it will run out of box on a Xeon Phi. You don't need to change the code, and you don't need to recompile the application. Of course, it will not achieve the optimal bandwidth, so this is probably not that interesting for computational applications. But it is interesting for applications such as the operating system. Indeed, you can run general-purpose operating systems, and there is official support for RHEL, CentOS, SUSE, and Windows on Xeon Phi. Some people also report success with Debian-based installations. Systems with Intel Xeon Phi processors are being built and shipping today, and you can get a server or a workstation with a Xeon Phi inside. In a server, well, you can see this is the cooling solution, and underneath it is the CPU. There are also memory slots. And if you look close enough, you will find that this is a PCI Express connector for optional networking. In a workstation, you will get similar hardware. So there is no coprocessor in the system. It is running entirely off the Xeon Phi processor. But in a workstation, you will also find an air or liquid cooling solution, which makes it quiet, and you will find additional PCI Express slots for additional devices. To learn more about these models, you can visit dap.xeonphi.com, and everything that you can find on this website is live and active as of today. The bootable form factor of Xeon Phi makes it very much like a standard CPU, but this is not the only form factor that is expected. Intel has announced that in November 2016 it will release the KNL-F form factor, which is a bootable processor with integrated fabric. So a high-performance interconnect will be fused onto the chip, and it allows you to build a cluster of servers with Intel Xeon Phi processors and connect them with a special interconnect that has very low bandwidth, very low latency and very high bandwidth. It is based on the Intel OmniPath architecture. Additionally, Intel is planning to release the coprocessor form factor of KNL. So this is going to be a PCI Express add-in card. It requires a standard CPU to work as a host, and it gives you the advantage of having multiple net-slending processors in a system with which you communicate via offload, or probably like in the first generation, using native programming. Xeon Phi processors seem like an excellent platform. They run the same code that a standard CPU runs, and they deliver high performance. It is important to realize, however, that this performance doesn't come for free. In fact, it takes good software to unlock the performance of a net-slending processor, and for that matter, of any parallel processor. Here's an example illustrating how it works. This is a very common story in applications. I'm demonstrating the performance of an n-body simulation. This is a toy model that we use as an exercise in most of our trainings. We run the simulation on a standard Xeon processor. This is a high-end model, 28 cores. Then we run this simulation on the first generation Xeon Phi processor with 61 cores. And finally, the same code we run on a Xeon Phi processor of the second generation. what we see is that if the application is not aware of the architectural details, then first of all, even on a Xeon, we get very low performance. And second, if we try to upgrade the hardware without modernizing the software, we actually see performance degradation. However, the situation changes once we start optimizing the code. When we make it aware of the multiple cores, when we make it aware of what kind of instructions the pipeline supports, when we optimize vectorization and memory access, we get much higher performance on all platforms. And I want to stress that across all of these tests, we use the same code in C++. Furthermore, we see that with the optimized code, upgrading upgrading hardware gives you performance boost. So we have made our software future-proof. You can learn more about this workload in chapter 23 of this new book. Performance optimization is important not just for computationally intensive applications. It is also important for applications that rely on memory bandwidth. Even if you look at the industry standard benchmark, such as Stream, and you run it without optimization out of the box, then you will get only a fraction of the nominal system performance. And only if you optimize the way that you compile this application and the way the environment in which you run, only then will you achieve the nominal bandwidth of the on-platform memory and the high bandwidth of the on-package MCDRAM. You can learn more about this particular optimization in episode 6 of this workshop. So just click down through the playlist. To understand how to optimize, it is important to understand what building blocks there are in the architecture. For example, what instructions the pipeline supports, what vectorization is and how to use it, how multiple cores like to cooperate, and how to effectively use caches and the main memory. If you are doing a distributed computation in a cluster, then you need to worry about the effectiveness of communication between multiple systems. We talk in detail about these optimization areas in our comprehensive 20-hour course, House Series. You can learn more about the House Series from episode 10 of this workshop. This is where I give the pointers to additional learning resources. In the course of this workshop, I will try to illustrate with enough detail what the building blocks look like for a Knights Landing processor, and I will look at it from the point of view of a programmer. So in the next 4 episodes, we will talk about cores, vectors, memory, and cache organization, and I will explain what it means to you as a software developer. Stay tuned for episode 2, where we will talk about cores in Intel Xeon Phi processors and multithreading.